we're recording, and then we'll share our screen. And all right, okay. So if you could, on your diagram, we're gonna draw a few things here. One is the Cartesian plane. So let's start with that. So we'll draw. That's not it. And you might want to draw this relatively large. And then we're going to draw a circle on top of the grid. So I have to do this kind of separately. So I draw a circle. I'm going to move it onto the grid. And it's pretty close. And so this circle could be the unit circle or really any circle you want. That down there. Turn my video off. There we go. So I'm just going to flip over so I can draw on this thing. There we go. Okay, so I'm going to get you to draw a terminal arm going to point P. Let's make point P here. And okay, I'll draw a green circle. That's cool. And I'm going to draw a line going from the center of the circle to point P. And let's give this point P coordinates x, comma, y. There's our coordinates there. And then we'll draw angle theta, like that, angle theta. And once again, this is, we'll use radians, pi over 2, pi, 3 pi over 2, and 2 pi. So sort of going back to our angles in standard position. And then if you look at your definition for sine, we know that the sine of an angle is y over r, the cos of an angle is x over r, and the tangent of an angle is y over x. And that stuff we've done since grade 10 and a good part of last chapter. But what we're going to look at now is what really is an identity here. So what is an identity? And there's many different types of identities. So I guess I probably should have said trigonometric identities, but an identity basically is just a true statement in math. And so if we look at, say, a term like cosecant of theta, we've learned that is really 1 over the sine of theta. And so that's just a definition in math, and that's actually referred to as an identity. So although I never called it an identity, it is an identity. And in fact, if you wrote sine theta, you could say that's really 1 over cosecant theta. So that would also be an identity here. Okay, thank you, Jessica. So that's one of our identities. So that would mean you actually know 2 other identities, one of them being secant, and the other one being cotangent of theta. So I'd like you guys to write out with which identities those ones are. That would be related to what we talked about last chapter. So secant of theta is just cos flip, so 1 over cos of theta. And cotangent is just 1 over the tangent of theta. So those are 3 identities that you kind of already knew before today, but maybe didn't know they were called identities. So that's just true statements in math that are true. So now the next thing we're going to do here, and this I'm going to take a little bit of time on this one. I know some of you might have done this with your other teachers in grade 11. I'm not sure how much in depth they went. But if I go back to my point P here, this point on the diagram, and I draw a line going straight down to the x-axis and put a little, oh, bless you. You might want to turn your mics off just because I think some of you might have your mics on right now. just in case you say something inappropriate, like, that Mr. Dixon guy, he's like, anyway. So if you look at our diagram here, on the bottom we have X, we have Y going up there, and then we have R there. And those purple letters, that's actually how we originally got sine, cos, and tan to be Y over R, X over R, and Y over X here. So what I want you to do is take the sign identity, the sign statement, and let's just rewrite that down here. And what I want you to do is to isolate the Y value of that. So just get Y by itself there, and do the same thing for the cos. And in this case, get the X by itself. So basically you'll have like Y equals something and X equals something. So if I bring the R up to the other side, I would get R sine theta equals Y. And over here, I get R cos theta equals the X value. So if I go up to point P again on my diagram, I'm going to zoom in a little bit here. I'm going to take a look at this point now. Actually, maybe I'll zoom out so you guys can see that. Sorry. And what I could look at now is point P. I could actually call it something different now. I could give it coordinates that are actually related to the radius of the circle and the trig term that goes with it. So the X value is actually R cos theta. So this point could actually be called R cos theta, and this would be R sine theta. And what I could do now is say that the X part down here, let's get rid of that X, and let's call that R, doesn't turn out very well. Let's call that R cos theta. And this Y value, let's get rid of that Y value and call that R sine theta. Okay. So I'm just replacing the X and Y with the trigonometric ratio you guys knew from grade 11 and grade 12. Now, if you go back to how we solved X, Y's, and R's in the last chapter, you probably remember the formula X squared plus Y squared equals R squared. And that comes from the Pythagorean formula, A squared plus B squared equals C squared. So it originates from that, and then we apply it to the unit circle. But remember that X now is R cos theta. So this would be R cos theta squared plus R sine theta squared equaling R squared. And if I square these terms, I would get R squared cos squared theta. I'll talk about how we write that. R squared sine squared theta equaling R squared. And so I'm going to make a little note over here that if you take cos theta and you square it, so that means like cos theta times cos theta, the way we write that in math classes is this way. We don't write it this way, because that actually means the angle is being squared. So we don't want to write it that way. So this way of putting the sort of the power in there, that means cos theta all squared. So here we have R squared cos squared theta plus R squared sine squared theta. And so what I'm going to do is I'm going to divide everything, both sides. I'm going to divide both sides by R squared. And of course, or you could say factor out the R squared and divide both sides by R squared. And what you get is probably the most important identity we're ever going to work with in math 12 is cos squared theta plus sine squared theta equals 1. And you can actually, if you have a calculator handy and you want to test this, if you just pick any angle you want, like it could be 20 degrees, it could be pi over 5 radians. And if you're in degree mode, you could just check this right now and go cos, let's say 15 degrees, and then square that, and then add that to the sine of 15 degrees, square that, and it's going to equal 1. And if you're working in radians, if you said cos of, let's say, pi over 7, then you square all of that plus the sine of pi over 7, all squared. That's going to equal 1. So it doesn't matter what the angle is. It's just you got to make sure you take the cos of that angle, then square it, and then the sine of that angle, then square it, and then add the two numbers up, and it'll always give you a value of 1. So this actually doesn't matter how big the circle is either. The circle could be really small, like a little tiny, maybe a wheel on the back of your bike where you have your sprockets and stuff. You could have a really small sprocket, or you could be talking about a giant Ferris wheel or something. It doesn't matter how big it is. This statement is always true. And so this statement we call the Pythagorean identity. Mainly because it comes from Pythagoras. It all sort of originated back here. That's where we got it from. So it's referred to as the Pythagorean identity. And then there's actually two other ways to write this identity, which are useful down the road. You'll see why they're useful. And that would be saying that cos squared theta equals 1 minus sine squared theta, and sine squared theta equals 1 minus cos squared theta. And once again, it may not make a lot of sense right now, like why that's useful, like how would you use that in the kind of math we're going to get into. But once you start practicing some of the questions, you'll see it's quite useful to think of it in one of these three forms. So I'll call this form 1, form 2, and form 3. So 3 different forms there. Okay, so let's go back to another really useful identity to get your head around, and that was that the tangent of theta. We said that the tangent of theta back in grade 11 was y over x, so it was the y value divided by the x value. But if you go back up to this part right here, and put a box around it, we've already determined that you can actually write the coordinates as trig terms. So the y value is r. The y value is r sine theta, and the x value is r cos theta. So if I go down here, I could say that tangent is equal to r sine theta divided by r cos theta, because really r sine theta is y and r cos theta is x. And now once again, just like in the above Pythagorean identity, you can divide by r's, so r's would cancel. And so this tells us that the tangent of any angle should equal the sine of that angle divided by the cos of that angle. And once again, if you use your calculator, let's say you're in degree mode, and you do the tangent of 45, that should equal the sine of 45 divided by the cos of 45. Gives you exact same answer, which turns out to be 1 in this case here. And then, of course, you know that cotangent of theta is really 1 over tan of theta, which means I should just flip the tan, which would give me cos theta over the sine of theta. So I'm going to work with these identities, and I'm just going to put a number beside them. So I'm going to use blue numbers now. So let's call this one 1, okay? And really, these are also 1. They're just different forms of it. And then I'm going to use 2 and 3 here. So these are different identities here. Okay. So let's take a look at what might look like a really confusing statement when you first get it. Let's say you had something like sine theta multiplied by tan theta multiplied by cos theta multiplied by, let's think, the cosecant of theta, okay? And you were asked to simplify this, because right now it doesn't look very simplified. And you're kind of like, well, how would I simplify that? What would I do to that to make it simplified? And so what you want to look at is identities. And in the beginning of this, it can be quite tricky to know which identity to use. But once you practice enough of this, it'll almost become second nature for you. Like you'll be like, oh, I should just turn it into that. So what I would say is, it's a suggestion, possible steps you could take is I would try to convert to sine or cosine. And the reason I suggest that is that if you're just dealing with sine and cosine, you're just dealing with two things, like two different things. But if you have like a tan and a cotan and a secant and a cosecant and maybe something squared, it gets really hard to figure out how you're going to manipulate it to get to the right answer. So if I see something that's in sine, I just keep it like sine. If I see a cos, I keep it like cos. But everything else I change right now. So I want you guys to take the statement we just wrote here, this sine, tan, cos, cosecant, and I want you to turn all those things into sines and coses if they're not already sines and coses. If that makes sense. So I'll give you just maybe 30 seconds to try that, and I will be right back. It's going to do the long journey to the end of the room here. Oh, it's so echoey here. See if I can find a math book. Okay, so let's take a look here at this one. So I'm going to keep the first sine as a sine theta. And now the tangent, I'm going to turn that into what it is, which is sine theta over cos theta, multiplied by cos theta. And then cosecant is really 1 over the sine of theta. Okay. And I guess you could argue these are over 1s. So when I multiply these 4 fractions out, you'll notice some things are going to disappear on us. So the coses are going to cancel. So you're going to lose your coses. And you're going to lose one of the sines upstairs here. So those are going to become 1, 1, 1, 1. So this really long, confusing looking statement will reduce down or simplify down to just a single sine statement here. And so this is one reason we use identities, is to try to take what may look like really crazy looking equations and being able to simplify them into something smaller, which usually is more helpful for us to move through. So let's take a look at another one, maybe one that's a bit more, just make sure I write the right one down here. That'll work. Yeah, there we go. So can we reduce or can we simplify this expression? Say 1 plus tangent squared x. We'll with theta, make it theta stuff. Okay. And so once again, we're going to see if we can somehow simplify this. It's not as crazy looking as the other one, but let's sort of see where we get to here. Okay. So I'm thinking, well, I know that's just 1 for now, and then plus. And now tangent I can rewrite as a sine over a cos, but I have to square it because it's tan squared. So that's going to give me sine squared theta over cos squared theta. Okay, so not exactly simplifying, really, looks kind of crazy. But let's think about that 1 first of all. We know that 1 can be written many different ways. So we can write 1 like 5 over 5 or 7 over 7. And what I'm going to try to do here, my second step suggestion, is to try to combine terms. If possible. Sometimes you can't, but I'm going to try to combine terms here. So I'm going to try to get the 1 and this tan to come together to be one thing here. So right now I know that the 1, I'm just going to write 1 over here. I know 1. I know 1's 1 over 1. So it's the same thing here. And if I want to combine a number with a fraction in addition, I have to have a common denominator. So my LCD here looks like cos squared theta. So I'm going to turn the 1 times the top by cos squared and the bottom by cos squared. So if I convert this into cos squared theta over cos squared theta plus sine squared theta over cos squared theta, I can rewrite that as a single fraction that has a denominator of cos squared theta. So let's do that, cos squared theta. And on top, I would have cos squared theta plus sine squared theta. Now, I'm not quite finished yet, but I just want to make sure we're okay with that, that we just turned the 1 into a fraction where you're basically have a denominator and a numerator that's the same thing. And the reason that I chose that, the reason I chose cos squared theta, is that the second fraction had a cos squared theta in the bottom. So I wanted to do that. And of course, you might be thinking to yourself, well, it looks like you made things way worse. Like you had this up here, that looked much nicer than this. It's like, scary, and it is. But if you think about that's actually, there's an identity there. There's an identity sort of glaring at you right now. Super sexy toga wearing identity, and that would be the Pythagorean identity. So we go up here, the first identity here. So this identity here, this is 1. Cos squared theta plus sine squared theta equals 1. So on top here, I just have a 1. Now, if this was a written question and you stopped here, I would agree with you, that's pretty simplified. But you could do one more step. I'm just thinking, if this was a multiple choice question, I would always simplify as much as possible. And we know that 1 over cos is the same as secant. So this would be the same as secant squared theta. And that's much more simple now in terms of the original statement. So we tend to do this manipulation of things, and it is a bit maybe overwhelming at first, a lot of different things you could do. But once you practice it, you'll start to see patterns emerge and emerge again and again and again. And probably the most common identity you're going to see, I would think, is this identity right here. And that is the Pythagorean one. So that's our Pythagorean identity, okay? So let's try one more, very, very similar identity. I'm gonna give you maybe a minute to try something here. But this one is not much different from the first one we just did. So let's go cosecant squared theta minus cotangent squared theta. And this one does simplify quite nicely, actually, for us. So we have cosecant squared theta minus cotangent squared theta, and just give yourself maybe 30 seconds and a minute and just sort of see where you get to with that one. Okay, so our first suggestion is to convert things to sine and cosines here. So the cosecant, that's just 1 over sine, but it's squared, so 1 over sine squared theta. And I know cotangent is tan flipped, and if you flip tan, you're going to get cos over sine. So cos squared theta over sine squared theta. And now I have two terms here, so, and I'm subtracting them, so I need to have a common denominator, which I do actually already have a common denominator, so I can easily combine these two terms. And that's going to give me 1 minus cos squared theta all over sine squared theta. Now, can you do anything else here? Is there anything else you could do, or are we kind of stumped at this point here? So my third thing I suggest is, so we did the sine cosine thing, we did the combine the term thing. And the third thing I would look for now is look for other identities. And once again, this is just a list of suggestions. They don't, I mean, it doesn't always work out for you sometimes, but this would be a good suggestion here. So 1 minus cos squared theta. So where have we seen that before? Well, if we scroll up, this number, this here, we've seen that before, cos squared theta plus sine squared theta minus 1 or equals 1. And so if we were to bring one of those trig terms over, we would get one of these equations here, right? So let's just go back down there again. So we had 1 minus cos squared theta. So we have 1 minus cos squared theta. That equals sine squared theta. So the top of this fraction is actually sine squared theta all over sine squared theta. And of course, since the numerator and the denominator are the same thing, this would equal 1. So this is a example where we seem to be reusing the Pythagorean identity just in a slightly different different form here. Okay, so let's try a couple different questions here. So that'll work. Okay. So sometimes we have to do some review of what may seem like basic math steps, but when they're applied in this chapter, they can seem like brand new things, really. And so let's say you had 1 over 1 minus sine x, and you were adding that to 1 over sine x. And what you were trying to do for some reason was this second step here. You were trying to combine these two terms here. And so when we start throwing trig terms around, I think what might seem like a fairly basic question, if I was to ask you this like in grade, maybe grade 6 or something, I said, 1 over 6 plus 1 over 5. And I asked you to add those two fractions. I don't think anybody's going to struggle too much with that. But with this, it can look a little, little more daunting. And so we have to look for LCDs here, the lowest common denominator. So in the example here, the LCD is clearly 30. And so I would times this by 6, this by 6, this by 5, this by 5. And that would give me 5 plus 6 all over 30, which is 11 over 30. And so with numbers, it's usually fairly straightforward how you do that. But for this question, this is tricky now, is the LCD here, well, you got to have a sign. You got to have a sign. So you have to have a sine x. And you also have to have a 1 minus sine x. So that would actually be the LCD for this particular question. So I times the right side, I guess, by 1 minus sine x over 1 minus sine x. And I times the right side, or sorry, the left side, by sine x times sine x. And now my LCD would be sine x, 1 minus sine x. So that's what they would all be over top of. So I've got this big long bar here. And I'm going to put my plus sign in. That's this plus sign. Okay. And so on the left-hand side, I have sine x times 1. So that gives me sine x. And over here, I have 1 times 1 minus sine x. And I guess I could tidy that up by saying sine x minus sine x is 0. So I'd have 1 all over sine x, 1 minus sine x. So this second step here in the notes right here, things to try, that can be tricky sometimes if you have fractions that have quite different denominators, especially one that's a binomial. So this one on the left-hand side, it's a binomial denominator, and that's a monomial denominator. So that can be a little bit trickier to work out there. Okay, so let's just try a few more. I got a little bit more time here. You guys are very patient. Of course, you're all muted, so I have no idea what you're doing right now. But let's try 2 more simplifying ones. Okay, so let's try 2 more simplifying. So once again, we're just working with those first few identities. So example, let's take 2. Is that too hard? You guys can handle that. 2 tan x all over cos x tan x plus sine x. And I'm just going to work through this right now with you guys, just because just looking at the time here. But once I'll sort of narrate as we're going through the things I'm looking for, or things I would suggest that you do. And the first thing I would look at is you can deal with tans, because we know that tan is sine over cos. So that might be one suggestion you look for. But let's sort of see where we get to here. So the tangent is the identity sine theta over cos theta. So we have 2 multiplied by sine theta over cos theta. So Mr. Lede, how's it going?
I'm doing well, Mr. Dixon.
Good. I have a guest now.
Are you doing a Zoom meeting?
I'm doing a Zoom meeting, yes. So, but I'm here just so they can see us. Hang on.
Maybe not to the screen share.
Oh, there we go. That's Mr. Lede. Hey guys.
Hey, while you're here, you can be witnesses.
Oh.
We wanted to thank Mr. Dixon for the extra work that he's doing to support kids, and as he comes back next week, and we're going to give him a little coffee card so that he can go out and enjoy a treat or a coffee at Cafe Fantastico. So give him a big thumbs up when you get a chance. All right.
My friend's brother opened that place.
Oh, really?
Yeah, that's cool. Yeah.
Anyways, we do appreciate it.
Thank you. Oh, no problem. Yeah. No.
And,
Yes. Thank you. I'm very excited now. So thank you, Mr. Lede. Okay, so let's. I'm going to turn my video off because I've been looking at my forehead. So let's take a look there. So we got tan theta, which is sine over cos. So we have 2. I lost my pen here. 2 sine theta, or x. Sorry, let's do that. All over cos x. That would be in the top, and the bottom would be cos x times sine x over cos x plus sine x. So it looks like, where are we here, that these coses would cancel, and that would give us 2 sine x over cos x. And then that's all over sine x plus sine x. But really, what is sine x plus sine x? It's like I got 1 apple, I got another apple, I got 2 apples. So let's say 2 sine x. So let's get rid of that. So sine x plus sine x, 2 sine x. And then we have to remember what we're dividing here. Remember that this bar right here, this bar here, that's your division bar, right? So you're saying that divide by that, so that divide by that, so that divide by that. So when I say that, which is 2 sine x cos x, and I'm saying I'm dividing it by 2 sine x, so I'm dividing it by 2 sine x. But when we work with fractions, we really want to multiply by reciprocals. So I'm going to skip a step here. I think you guys can handle this. So if I'm dividing by 2 sine x, that is the exact same thing as multiplying by the reciprocal 1 over 2 sine x. So when you divide by a number, it's the same as multiplying by its reciprocal. And the reciprocal of 2 sine x is 1 over 2 sine x. And I think you can clearly see now you're going to get even more simplifying here, because the 2 sine x will cancel the 2 sine x, and that gives you 1 over cos, which is simplified. But we could go one more step, I think, because cosine, if it's flipped, is the same thing as secant. So this would be the same as the secant of x here. Okay. And then I did say we're going to do one more, to do 2, sorry. So this would be our second one, and we'll finish here. So let's do one more example here. So let's pick one that looks terrifying. Boy, that looks pretty scary. This is sort of extreme difficulty. Okay, so maximum effort would be needed here. 1 plus sine x all over the secant of squared x times 1 plus cosecant x minus tan of x times the secant of x plus the tangent of x. I'll just let you, just even writing that down is painful. So just double check. Cosecant x, 1 plus sine x, secant x, 1 minus 1 plus cosecant x minus tan x. Okay, there we go. Holy yikes. Okay, so I'm thinking there's way too much stuff to look at here the way it is. So I might be tempted to convert to sines and coses, which narrows down the things that will happen. Sometimes you can do factoring first. So I'm just going to put a little star here. I don't think that's going to work in this question, but sometimes you might actually be able to factor something out and reduce first. But I don't see anything clearly that I can factor here. So let's do our changeover here. Let's change everything. And it does always look bad before it gets better. And I think that's like a proverb somewhere. So cosecant is 1 over sine of x. And I'm multiplying that by 1 plus sine of x. That's actually over 1. And then this is going to be a nightmare. All over. Secant is cos, so that's going to be 1 over cos squared of x, multiplied by 1 plus cosecant, which is really 1 over sine of x, close that, minus tangent, which is really sine of x over cos of x, multiplied by secant, which is 1 over cos of x, plus tangent, which is sine of x over cos of x. And I'm just going to double check that because this is awful if it wasn't true. And if you guys see something glaringly wrong here, please let me know, because I'm trying to drink as much Coke as I can. I think that's Coke. Anyway, so 1 plus 1 over sine over cos, 1 over cos, sine over cos. Alrighty, okay, so let's do the numerator part here. So the numerator is this part here. So I would get 1 plus sine x all over sine x. And on the bottom, or the denominator, probably use the proper words here. I've got to do some serious distribution here. So I'm going to get, where are we here? I'll use purple again. So I'm going to get 1 over cos squared x plus 1 over cos squared x sine x minus, and then I get sine x over cos squared x. And then I get minus, because you gotta distribute that negative into both. So I get minus sine squared x over cos squared x. Does that make sense? I think that makes sense. Oh, there was an easier thing to do. Oh well, doesn't matter. I'll keep going. Okay, so let's take a look here. So let's carry that down. There was actually a factoring thing we could have done here, but I was not thinking. Okay, sorry. So let's see if we can tidy this up a little bit here. So we've got where is it here? Cos squared. Yeah. Okay. So, so one thing we could bring together is 1 minus sine squared x minus sine x all over cos squared x. So I'm bringing together the 3 cos squared x's. And on the end here, I'm going to write in my plus 1 over cos squared x sine x. That's right. Okay. And this part here, I could write that as cos squared x minus sine x all over cos squared x plus 1 over cos squared. Actually, I need to erase that. Sorry. Because on top I have my 1 plus sine x all over sine x. On the bottom, I would have cos squared x minus sine x all over cos squared x plus 1 over cos squared x sine x. So I'm going to need to times this fraction by a sine x. And this is looking dreadfully awful. And the bottom, that's going to give me sine x cos squared x minus sine squared x all over sine x cos squared x. And then I had this plus 1 over cos squared x sine x. So I'm going to, just looking at the time here, I'm going to stop here because I'm sad, very sad with myself. So this question, I think might be too hard, but I was looking for up here, at this part here, there's actually, you can create some 1 plus sine x's and do some factoring here. But I think this one obviously looks a bit on the insane side. So I'm going to stop there. And I will definitely not give you that question to do or one that's that crazy, okay? But I think I made a mistake somewhere in my math here. I'm just looking at the time and I feel bad. So anyway, so let's switch back and let me just stop the recording.